Ever wondered if quantum computers could one day replace the traditional ones we use today? Let's dive into this fascinating world. Quantum computers aren't just an upgraded version of our everyday computers. They're a whole new beast, operating on the principles of quantum mechanics. Unlike traditional computers that process bits in sequences of zeros and ones, quantum computers use quantum bits, or qubits, that can be both 0 and 1 at the same time. This superposition allows quantum computers to process information at an exponential rate. Imagine solving complex problems which would take a classical computer millions of years in a matter of seconds. Sounds like a sci-fi movie, right? But it's not. It's a reality that's unfolding right before our eyes. So, are quantum computers the revolution we've been waiting for? Or are they just overhyped? Indeed, quantum computers promise a new era of computing, but how do they work exactly? Quantum computers operate on the principles of quantum mechanics, a field that even Einstein referred to as spooky. Sounds intimidating, doesn't it? But let's break it down in simple terms. Imagine a coin. In the classical computing world, this coin can either be heads or tails. There's no in between. But in the quantum world, it can be both heads and tails at the same time, thanks to a principle known as superposition. It's like having a coin spinning in midair. Until you catch it, it's both heads and tails. This is a game changer because it allows quantum bits, or qubits, the basic units of quantum information, to hold more information than classical bits. Now let's talk about another principle: entanglement. Picture a pair of gloves. If you pull out a left glove from your drawer, you instantly know the other glove is a right one, no matter where it is. In quantum mechanics, two particles can become entangled and behave like those gloves. If you measure one, you instantly know the state of the other, even if they're light years apart. This spooky action at a distance, as Einstein called it, allows quantum computers to process information in a profoundly different way than classical computers. Finally, there's quantum tunneling. Imagine you're hiking and there's a mountain in your path. In the classical world, you'd have to climb over it. But in the quantum world, you can tunnel through it, saving time and energy. Quantum computers use this principle to find shortcuts through complex calculations. So, what's the big deal? Well, these principles allow quantum computers to process multiple solutions simultaneously instead of one by one, making them incredibly powerful. Imagine solving a maze by exploring every possible path at once. That's the power of quantum computing. So with these principles, quantum computers can process multiple solutions simultaneously. But what does this mean in practical terms? Imagine being able to solve a problem in seconds that would take a traditional computer thousands of years. That's the potential of quantum computing. This isn't just theoretical talk. Quantum computers are already making waves in various fields. Take drug discovery, for instance. Quantum computers can simulate the behavior of molecules, helping scientists understand how drugs interact with our bodies and potentially leading to the development of more effective treatments. Then there's climate modeling. Quantum computers could help us create more accurate models of our planet's climate, allowing for better predictions and ultimately, more informed decision-making about how to tackle climate change. And let's not forget about encryption. Quantum computers could break many of the encryption techniques we use today, making our digital world more secure. But they could also create new, more secure encryption methods. Quantum computers could revolutionize countless fields, but they're not without their challenges. Like any emerging technology, quantum computers face significant obstacles. So, what are they? First, there's the technical aspect. Quantum systems are incredibly delicate and susceptible to environmental interferences, making them challenging to stabilize. Then, there's the cost. Building and maintaining a quantum computer is an expensive endeavor, often running into millions of dollars. Next, we have the human element. Quantum computing requires a highly specialized skill set. There's a scarcity of quantum physicists and engineers who can design and operate these machines. But as with any challenge, there's also an opportunity. As we invest in education and training, we can cultivate a new generation of quantum scientists and engineers. Despite these challenges, the future of quantum computing shines brightly. It promises to solve complex problems far beyond the reach of classical computers. From developing life-saving drugs to predicting climate changes, the potential applications are limitless. Quantum computing stands on the precipice of revolutionizing our world. Are we ready for this quantum leap?